In July of 2023, a single wrong command sent Voyager 2 spinning 2 degrees off course. And just like that, humanity lost contact with a spacecraft more than 12 billion miles from home. For 2 weeks, engineers at NASA genuinely did not know if they would ever hear from it again. When Voyager 2 finally woke back up, buried inside the data streaming back to Earth, was something nobody on the mission team had fully expected. If you have ever wondered what it actually takes to lose and then somehow find a machine that far away, stay with me, because this story has everything: human error, a desperate last resort gamble, and a genuinely strange discovery hiding in the data the moment contact came back. By the end of this video, you will understand exactly what went wrong, how NASA pulled off one of the most nerve-wracking rescues in the history of spaceflight, and why what Voyager sent back afterward made scientists sit up and pay very close attention. Let's start with the spacecraft itself, because Voyager 2 is not just old, it is genuinely one of the most remarkable machines humanity has ever built. Launched in August of 1977, just weeks before its twin, Voyager 1, Voyager 2 remains the only spacecraft in history to have ever visited all 4 of the outer gas giants: Jupiter, Saturn, Uranus, and Neptune. Its flight path took advantage of an extremely rare alignment of the outer planets that only happens roughly once every 175 years, allowing engineers to use the gravity of each planet to slingshot the spacecraft onward to the next. A trick that saved years of travel time and an enormous amount of fuel that a spacecraft this size could never have carried on its own. After completing that grand tour by 1989, it kept going, drifting steadily outward, and in November of 2018, it officially crossed into interstellar space, becoming only the second human-made object ever to leave the protective bubble of our sun's influence entirely. By July of 2023, Voyager 2 had traveled more than 12,300,000,000 miles from Earth, a distance so vast that a radio signal traveling at the speed of light takes 18.5 hours just to reach it, and another 18.5 hours for any reply to make its way back. Now here is where everything went sideways. On July 21st, 2023, the flight team at NASA's Jet Propulsion Laboratory sent what should have been a completely routine set of commands to the spacecraft. Somewhere in that batch of instructions, something went wrong, and the antenna Voyager 2 relies on to talk to Earth, called the high-gain antenna, ended up pointed just 2 degrees away from our planet. 2 degrees might sound like nothing, a rounding error, barely a nudge, but at a distance of 12 billion miles, even that tiny misalignment was more than enough to break the connection completely, since a radio beam that precise spreads out and weakens dramatically over such an enormous distance, meaning even a small angular error translates into the signal missing Earth by an almost incomprehensibly large margin by the time it reaches our part of the solar system. Voyager 2 could no longer receive commands from mission control, and it could no longer send data back to Earth. The spacecraft had effectively gone deaf and mute, all because of a shift smaller than the width of your thumb held up against the night sky. For NASA's engineers, this was not a minor inconvenience. This was one of the most serious crises in the entire Voyager program's 46-year history. Voyager 2 is irreplaceable. There is no backup spacecraft sitting in a warehouse somewhere that can simply be launched to take its place, and there is absolutely no way to send a repair crew 12 billion miles into interstellar space. If the antenna stayed misaligned permanently, the mission would essentially be over, with Voyager 2 continuing to drift silently through the darkness forever, alive, but completely unreachable, still carrying its instruments, its power source, and its golden record, but with no one on Earth ever able to speak to it again. The first small flicker of hope came on August 1st, when engineers at NASA's Deep Space Network, the global system of massive radio dishes used to communicate with spacecraft throughout the solar system, managed to detect something. It was not real data. It was what engineers call a carrier signal, sometimes nicknamed a heartbeat, essentially just a faint hum confirming that Voyager 2's transmitter was still powered on and functioning, even though its antenna was aimed in the wrong direction. It was a bit like hearing someone's phone still ringing somewhere in a dark house, without knowing if they could actually hear you calling their name back. With that faint heartbeat detected, the team decided to try something dramatic. On August 2nd, the Deep Space Network's massive dish in Canberra, Australia, the only facility on the planet with a direct enough line of sight to reach Voyager 2 at all, fired off what engineers informally called an interstellar shout, a signal broadcast at 100 kilowatts of power, dramatically, stronger than a routine command, aimed directly at the spacecraft's last known position. The goal was simple in concept and terrifying in practice: to essentially yell loud enough across 12 billion miles of empty space that Voyager 2 might still pick it up despite its misaligned antenna, and respond by nudging itself back into alignment with Earth. There was no guarantee this would even work. The spacecraft's antenna, after all, was not pointed toward Earth anymore, meaning even a signal that powerful had to somehow reach a receiver that was, technically speaking, listening in the wrong direction, relying on the sheer strength of the transmission to be picked up at all through whatever partial sensitivity remained at that awkward 2-degree offset. Because the one-way travel time for that signal was 18 and a half hours, and because any response would take another 18 and a half hours to come back, the team then had to do the hardest part of all. They had to wait. 37 hours of pure uncertainty with absolutely nothing to do but sit with the knowledge that either the gamble had worked or it hadn't, and there was no way to know which until the silence finally broke. Mission engineers describe those hours as some of the longest of their careers, since unlike almost any other engineering problem on Earth, there was no way to run a diagnostic, check a secondary sensor, or send a follow-up command to speed things along. The only option was to wait for light itself to finish making the round trip. At 12:29 in the morning Eastern Time on August 4th, it broke. Science and telemetry data began streaming in from Voyager 2 again, confirming the spacecraft was healthy, correctly oriented, and still exactly on its expected trajectory through interstellar space. The interstellar shout had worked. Engineers who had spent 2 weeks bracing for the possibility of losing one of humanity's most historic spacecraft were suddenly celebrating instead. It is worth noting that this was not even Voyager 2's first brush with silence. Back in March of 2020, the same camera antenna, the only dish on the planet capable of reaching Voyager 2 directly, was taken offline for a scheduled 11-month upgrade, leaving the spacecraft completely unreachable for the better part of a year. Voyager 2 sailed on through that entire stretch with no ground contact whatsoever, programmed in advance to simply keep functioning on its own until humans on Earth were ready to listen again. While we are talking about a spacecraft tough enough to survive months of total silence in the vacuum of interstellar space without anyone checking in, if this kind of real, verified space engineering story is what keeps you watching until the end, go ahead and hit that like button and subscribe if you have not already. Because the story does not stop with just getting the signal back. Here is where things get genuinely interesting, and where the phrase, something unexpected, actually earns its place in this story. Voyager 2 was never designed purely to survive and phone home. It was designed to keep measuring the actual physical properties of the region it travels through. Magnetic fields, cosmic ray levels, and the density of plasma, the electrically charged particles that drift through the space between stars. Each spacecraft carries an instrument called a plasma wave subsystem, originally. Built in the 1970s using entirely analog electronics, capable of detecting the natural oscillations that charged particles produce as they drift and collide in the surrounding environment. Scientists can use the frequency of these oscillations to calculate the density of the material Voyager is currently passing through, essentially turning a radio instrument into a kind of cosmic densitometer. And in the years surrounding these communication struggles, both Voyager 1 and Voyager 2 sent back a discovery that genuinely surprised the scientists studying the data. Using the same instrument aboard each spacecraft, researchers found that the density of material in the very local interstellar medium, the region of space immediately surrounding our solar system, was noticeably higher than existing models had predicted, and that this density appeared to increase steadily the farther the spacecraft traveled from the edge of our sun's heliosphere. This might sound like a small technical detail, but to the scientists studying it, it was genuinely puzzling. Researchers had generally expected interstellar space to either stay roughly consistent in density or to thin out gradually, the farther a spacecraft traveled from the sun's influence, based on existing models of how the heliosphere interacts with the surrounding interstellar medium. Instead, the data showed the opposite, a rising density gradient, suggesting there is some larger, previously unrecognized structure shaping the immediate interstellar neighborhood around our solar system, in ways nobody had fully mapped out before. Scientists involved in analyzing this plasma data described it as a large-scale feature of the very local interstellar medium, something that appeared consistently in data gathered by both Voyager spacecraft independently from 2 different directions, which made it far more difficult to dismiss as some kind of instrument quirk or isolated fluke unique to one probe. Researchers published these findings in the Astrophysical Journal Letters, a peer-reviewed scientific journal, meaning this was not a casual observation floated in a press release, but a result that had been checked, verified, and scrutinized by other scientists in the field before ever being publicly announced. Think about what that actually means for a moment. 2 nearly 50-year-old spacecraft, built using slide rules and technology that predates the modern calculator app on your phone, managed to detect a genuine, previously unknown structural feature of the space surrounding our entire solar system, simply by patiently measuring plasma oscillations for years on end while drifting further and further from home. Nobody sent Voyager out there specifically hunting for this. It emerged naturally from the extraordinarily long, extraordinarily patient dataset. These 2 spacecraft have been quietly building since the 1970s, a dataset that literally could not exist any other way, because there is no other way to directly sample interstellar space except by physically traveling there with an instrument capable of measuring it, and nothing else humanity has ever built has traveled that far. This is really the heart of why losing contact with Voyager 2, even briefly, felt like such high stakes for the scientific community, beyond the obvious emotional weight of nearly losing a piece of irreplaceable history. Every single day these spacecraft are still transmitting is another data point in an experiment that took literally decades just to begin producing results. An experiment. Measuring conditions that no other instrument in existence, on Earth or in any other spacecraft currently operating, has any ability to measure directly. If Voyager 2 had been lost permanently during that July 2023 antenna mishap, humanity would have lost half of its only two direct, ongoing sources of information about what interstellar space is actually like beyond the edge of our own solar neighborhood, with no realistic way to replace that lost perspective for decades, since building and launching a comparable interstellar mission from scratch would take many years just to reach the same distance Voyager 2 already occupies today. There is also something worth appreciating about how these two spacecraft essentially act as a matched pair of eyes looking outward from our solar system in two different directions at once. Voyager 1 exited the solar system heading up and out of the plane where most planets orbit, while Voyager 2 took a different route, angling downward and outward on a separate trajectory. That geometric separation turned out to matter scientifically far more than anyone could have guessed back in the 1970s, because it means the density gradient discovery was not just one spacecraft's lonely, unconfirmed reading. It was two independent measurements taken from two different regions of nearby interstellar space, both showing the same unexpected rising trend, which is exactly the kind of independent confirmation that turns a strange anomaly into a genuine scientific finding worth taking seriously. Power remains the real, unavoidable limiting factor for how much longer this story can keep being written. Both Voyager spacecraft run on radioisotope thermoelectric generators, devices that convert the natural heat of slowly decaying plutonium into electricity, and that decay happens at a fixed, unstoppable rate no amount of clever engineering can pause or reverse. Usable science data before another onboard instrument has to be shut down for good. That decision alone illustrates exactly how thin the margins have become on this mission. A voltage regulator exists specifically to protect delicate electronics from power fluctuations that could otherwise damage them permanently, and choosing to switch it off is essentially a calculated bet that the benefit of extra operating time outweighs the small but real risk of a damaging power spike somewhere down the line. It is the kind of unglamorous kind of bravery, engineers choosing to accept slightly more risk today in exchange for a few more years of eventually, and everyone on the mission team already knows this, there will not be enough electricity left to power even a single remaining instrument. When that day arrives, Voyager 2 will not send a final dramatic message or a farewell transmission. It will simply go quiet, mid-sentence, in the middle of whatever measurement it happened to be taking at the time, and continue drifting silently outward through the galaxy carrying its golden record, its recorded greetings in 55 languages, and its collection of music meant to represent all of humanity, for what will effectively be forever, or at least for as long as anything built by human hands can be expected to last. So, to bring this back to where we started, no, nothing paranormal or extraterrestrial happened when Voyager 2 woke back up in August of 2023. What actually happened was a very human mistake. A routine command that went slightly wrong, followed by one of the most tense patient rescue efforts in the history of space exploration, involving a signal shouted across 12 billion miles of empty space and 37 agonizing hours of waiting to find out if anyone was still listening on the other end. And once that connection was restored, the ongoing flow of data from Voyager 2, alongside its twin, kept adding to a genuinely unexpected discovery about the structure of the space directly surrounding our entire solar system, a finding that nobody could have made any other way, because nothing else humanity has ever built has traveled far enough to check. That, honestly, might be the most quietly remarkable part of this entire story. Two machines built in the 1970s, using technology that today looks almost primitive, are still actively rewriting our understanding of the space beyond our solar system, One faint radio signal and one painstakingly measured plasma reading at a time, decades after anyone involved in building them could have reasonably expected them to still be working at all. If this kind of deep dive into what actually happened out there, backed by real documented engineering and real published